All right, good morning. Hi everyone, welcome back to COMP526. Same game as every time. I'll start with a quick round of announcements while you can repeat the question about the programming puzzle, and then we'll look at that potentially. Number one, as I said yesterday, I have put this mock exam online on Canvas. Please have a look in some free minute. Play with it a little bit so you see what the questions in the exam are like, and you see what the technical setup for the exam will be like. It's set up as essentially a very identical copy to the final exam, except for the questions and the timing, which probably is obvious. You will see that also among the quizzes, there is the entry for the actual final exam. It's already in there, but you can only access this on May 28th. We are reaching the end of this module. Some of you found this a sad occasion. Maybe others are looking forward to the break. Be it what it may, it's coming, and what comes with it is the end of module survey. It's already online, but I will reserve some time next Tuesday to do that together. So I can encourage you to do it on the spot. And maybe we can discuss if some of the questions are unclear or so. I think it's useful to do this together. I haven't yet made up my mind what format the class should be next week because we're reaching the end of the presentation part. Maybe we'll switch over to just a Zoom meeting instead of the live stream. I'll let you know in an announcement closer to the day, depending on how fast I go today also. We'll talk about programming puzzle 2 in a second, and here's the upcoming deadlines. Same as yesterday, the only new one is I want to put out another class test, because so far the focus has been a bit unduly on the first part of the material. It's just naturally coming from the fact that there was some delay in getting the class test started because we first cover material, but I do want to have at least one class test covering the last third of the module. So I'll put up another one with due date next Friday. These are all quick and easy, and many people scored very well on those. It's actually a good way for you to boost your marks. I think having another one there is a good idea. Okay, programming puzzle 2, the exam cheat code, right on topic. This looks a little different from yesterday. Let me check how many people are tuning in at the moment. That's a bit at odds to what I see. YouTube claims there's only 9 people watching, but 13 have voted. So unclear what that means. Maybe I can't trust the setup so much, or people vote without being present in the video. That sounds a bit weird too. Okay, I'll just leave it open for a second, but thanks for the many people who have taken my advice from yesterday and now have started looking at it. If you don't really know what you're supposed to do, maybe it's a good idea to briefly discuss this together. So let me open the website for that. So you know this website well. Might be a bit small. So here's the description. I suppose this little scenario that I write there is clear enough, but maybe the coding part, how to actually implement this in Python, maybe not so clear. You should practice reading such formal specifications like I gave it here. This is essentially the unambiguous way how computer scientists specify these questions. So your task is to take an arbitrary vector of 20 bits, compress it to a vector of 10 bits, and then decompress it. And the task is to guarantee the best overlap, right? Because the decoding is what you enter as marks on the test, or what your sweetheart enters as marks on the test. So the number of correct bits that are the same in the encoded and then decoded message that are the same as in the original bit vector, that is the final mark, and that's what you want to maximize. But here you want to give a guarantee that is as good as possible for any possible bit vector of B of inputs. So you start with an arbitrary pattern of yes and no for the questions, for the 20 questions, and you want to know the best guarantee. You can always do simple tricks to guess, in many cases, many answers correctly, but that's not really good enough for this task. What we're after here is a code so that no matter what happens, no matter what yes and no patterns happen, you can guarantee 10 correct answers, for example. I don't know if this helped clarify it. Maybe you can use the Q&A tab instead, if that, to signal if that is any better now. If you look at the Python code, you see that it uses basically a list. So you're supposed to take a list of 20 bits, transform that into a list of 10 bits, and you're also supposed to write in a decoding method that's given any 10-bit vector and is supposed to produce a list with 20 bits, 0 or 1. That's what I mean by bit. And then the algorithm just tries them all and takes the worst result that you achieve in this. Okay, any clearer now? Okay, so this is, the rest is all just about how it's marked. I guess that's separate from the actual task. Now, I wonder if people want a tiny hint before we get started. So here's one hint that in the past has helped people with problems like this. It may sound very generic, but it is actually the key to get in the right direction. I don't want to give the solution away. I want to just send you on the right track. So this problem has parameters that are fixed. It has 20 questions and it has 10 bits that you're allowed to transmit, or you compress the 20 bits into 10 bits. You can have a look at the problem in a more general setting where you have a certain number of bits at the beginning, Q questions, and then H honking bits. At the moment, Q is 20 and H is 10. My hint is start with a very simple setup where these numbers are much smaller. And think about starting with 1 or 2 or 3 for these numbers. Which configurations, which choices for Q and H make the problem very easy to solve, where you can also see that you can do a certain guarantee, and this is the best you can hope for, because you can just exhaustively go through all possibilities for these small cases. Try to get started with that, with the small cases, and then see whether you can generalize this to the fuller instances. My promise is the answer will be yes and no. On the one side, you cannot directly apply the same tricks that might work for the small instances. But you can combine things you learned on the small instances very well into a solution for the problem as it is stated. Okay, maybe that was cryptic enough to not help you so much at the moment. I'll watch the leaderboard and see how people get along. A small number of people that have already run ahead and published their results there, but it's a very low number at the moment, and I'd like to see many more people submitting there. I would also add the hint that while the problem in general can be tough and it's open-ended, it's not necessarily obvious what is the optimal number you can get. There are some easy, low-hanging fruit. You can get a certain number of questions very easily without much thinking. I want at least every one of you to get that number in the submission. Maybe that's enough for today. We could do some last-minute discussion of that next Tuesday. I hope that the discussion mostly moves to CampusWire at this stage. You know the platform by now. You know how to ask and answer questions there. I don't want you to share the answer there, but if you have fundamental questions, like you don't understand what is really asked of you to do in this puzzle, CampusWire is the way to get a quicker answer than if you randomly email one of us, Ben or myself. Good, I think that's all on announcements. If you have any questions, then put them in the Q&A tab. Otherwise, I would like to continue with our last topic. There are no questions at the moment, it seems. So if that's the case, then let me move on. So very quick recap. We started talking about the range minimum problem. I said this last unit is a bit of a trip closer to current research topics on a very specific little niche topic. And it's a very simple and fundamental problem where you're just asking in an array to find the minimum in a certain range. The problem only gets challenging by the side conditions, if you like. We want this to be very fast at query time, and we allow ourselves some pre-processing time of the array to make that possible. But we really want a very fast solution, constant query time, and linear pre-processing time, essentially the best you can at all hope for. But we'll today work towards achieving that. A little side remark, is the audio fine? Is the audio as good as always, or is the mic too loud? Because I see it's occasionally dipping into the red region. Maybe some of you can either use the lecture back channel on CampusWire or the Q&A to let me know if something's wrong. I could maybe tune it down a little bit just to be on the safe side. Okay. It's probably still loud enough. And okay, thanks. Seems fine. Well, the question is now, is it better now that I turned it down or not? But I assume if you don't let me know, then you can still hear me fine. So I'll just leave it on the safer setting a little bit muted down. We already discussed the applications of RMQ. I'll skip this. It was the connection to the longest common extension problem that we left open at the time in Unit 6, how to solve that in this linear preprocessing constant query time setting. And we discussed two very simple, two trivial implementations of range minimum queries. This is where we left off. So yeah, any last questions, any last comments on audio quality, and then let's go. All right. We left off in the last video after discussing these very trivial solutions where you either don't do any pre-processing. That was the scan-on-demand solution. Whenever someone asks for a arrangement query, you just scan the range in the array. That's fine, except that the range can be the entire array, and so the query time is not that great. The opposite extreme was we pre-compute every possible query because there's essentially n² choices for I and j, n² over 2 because they're ordered, but let's not be too picky. You have essentially a quadratic number of choices of range minimum queries for a given array. So we might as well pre-compute the answers to all of them and store them in one big array. That was the pre-compute all solution. The query then becomes trivial. You just look up the corresponding value, but the pre-processing time goes up. Cubic naively, but you can do it at least in quadratic time if you're a little smart on it. But of course, that's not quite good enough. These two solutions are simple. How can we possibly improve upon that? It seems you have to do some storing of pre-computed values to get along, but how can you save on the space? And notice here, this running time of the pre-processing step is as good as possible as long as we store all of the solutions. We already spent just a constant time per entry of this array. So the time of pre-processing is basically dominated by the time we need to write the results, to write our data structure, which consists of this large array. So the question can also be phrased as, how can we reduce the space usage of this data structure? And that's what we'll look at next. There is one simple, nice trick that's not very complicated, but it does get a significant reduction in the space. And that's the first non-trivial idea on this topic. So let me also slow down a little bit, despite all the coffee I had. We'd like to do something like the pre-compute all solution, but we don't want to keep all entries. We need to reduce the space. So we only store the entries, the minimum index for I and j, for certain combinations of I and j. Namely, if the length of the range that we span is a power of 2. That's what this condition expresses in formulas. But really it says only if I and j have distance a power of 2, we store this entry. For any other ranges, we don't store the entry. We still have n choices for I, but then for any fixed I, we only have log n choices for j, because the total length is n. There's only roughly log n powers of 2 between the numbers 1 and n. So the number of entries is n log n instead of quadratic. That's a significant achievement. And there's even a smart way to store these entries by choosing a different index. Instead of choosing beginning index and end index, we now choose beginning index and power of the length of the range, right? That's the same k as here. But that's not the tricky part. The tricky part now is we only store a couple of these entries. How can we still solve any possible arrangement query? So how do we do this? It's fine that I'm hiding part of the solution at the moment. I want you to focus on the picture first anyways. The trick will be that we can use the information to puzzle together the answer of the overall query from a small number of queries that we do have. And in this case, this red range is the actual query we're interested in. And it stretches from 5 to 18, so that's a length of 14, if I'm not mistaken. And that's not a power of 2. 14 is not a power of 2, so we don't have this value pre-computed. What we do have is, starting at I, we have the 8 length range. That's the blue one. And we have this green range, which is also length 8. which ends with 18, with position 18. Now, in general, we can always find some power of 2 that's between the total length of the array. If we have exactly a power of 2, we don't need to do anything smart. At the other extreme, it could be so that we just touch with the green and the blue part. Actually, they always overlap by 1, otherwise you would have a next smaller power of 2. But it doesn't really matter. It would be enough if they just touch. So how can we puzzle together our arrangement query from this? Well, it's easy. The minimum in the overall red range must be somewhere in that range by definition. And in particular, it can be in the blue range, or it can be in the green range, or it can be in the overlap. But no matter where it is, it's either one of 2 numbers. It's either the minimum of the blue range or the minimum of the green range, right? That's the property of the minimum. If I have the smallest number in the blue range and the smallest in the green range, I can compare those two, and then the smaller is also the minimum of the entire red range. And so that's spelled out here a little bit more carefully with the indices worked out. We define our k like this, so that we have a power of 2 that's between the length of the range and half of that. And then we can cover this range by 2 ranges that have a power of 2 in length, a blue and a green one, as shown in the picture. You can work out what their indices are. And then the arrangement query, the red big query that we're interested in, so this is the red box, that is the smaller of these 2. So it's, well, argmin says it's either RMQ1 or RMQ2, whichever makes A of RMQ1, RMQ2 smaller. Okay, so that's just a fancy way of writing. If this is smaller, then return RMQ1. If A of RMQ2 is smaller, return RMQ2. And these 2 are just the arrangement queries from the blue and the green range. And these we have stored. So we can use our lookup table to obtain the answers to the green and blue recursive query. It looks recursive, but it's not really recursive. This is something we've stored in our table. And to be explicit, we could actually give the exact entry here if we had the space. Maybe I put that here. So we take the starting index in the first coordinate, and then the second coordinate is just the length. So that's actually easier than specifying the arrangement query. And we can do the same thing for the other one. Here it's not quite as nice because we have to copy this nasty expression for the starting index. But still not too bad. That way. So this is just 2 table lookups. And then finding which one is smaller is just looking at these 2 positions in the array and returning the smaller one. That was still fairly easy to do, right? But we got the space down from n log n, from n squared to n log n, at the expense of making the query twice as expensive if you want, but it's still a constant and a small constant. Instead of returning just 1 entry from an array, we take 2 entries from a table and compare the array entries. That's still very efficient. I haven't talked about the pre-processing so far. This was just how to solve the queries if we already have this 2D array M prime computed for us. If you think about it, the pre-processing is very similar to before. We can reuse the information that we've already computed to speed up the process, the pre-computation. If we would do it naively, so maybe this is worth writing down. If we would do it naively, we're essentially still paying a linear cost for some of the entries. So if we would just find the minimum in each step, we would have n times the size of the table. And that's still quadratic and actually a bit more. It's not as bad as the cubic that we've had before, but it's also not quite what we want. But we can do it smarter by exploiting, again, the recursive structure of arrangement queries. If I have a range I up to I plus 2 to the k, then I can always chop that up into 2 halves. So there's a first half and a second half. And these are actually already computed, because this one goes from I to I plus 2 to the k minus 1 minus 1. So that is just m prime of I and k minus 1. And the second range similarly is m prime of I plus 2 to the k minus 1, and then k minus 1. So I can do the same trick that I do in the query. Instead of recomputing the minimum in the large black range from scratch, I can use that I've already computed the minima in these 2 smaller ranges, and then the minimum in the big one is either the minimum of that range or the minimum of that range, and I can find out which one it is in constant time. So we've used the same trick twice, both in preprocessing and in answering queries. If you have a big range, you can decompose it into 2 parts if they are touching or overlapping. The important part is they have to cover the entire range. And you've already computed the minima in these ranges. You can just take those minima and compare them instead of the entire range. That will be the key technique to speed up arrangement queries, also in the more sophisticated solutions that we'll cover next. But it's important that you understand this part here in the sparse table solution, where it is still fairly nice and clean. The 2 subranges are always a power of 2, hence you've already computed it. For the preprocessing part, we just have to make sure that we compute things in the right order. So going from the small ranges to the big ones, that was the same in the last part. The precompute all solution also needs, for this n squared preprocessing time, you also need to compute the solutions in the right order, but that's easy to do. And with that, we get an n log n preprocessing time constant query time solution. That's already not too bad, but we can do better than that. And in particular, n log n is still a substantial overhead in terms of space. It's not only the preprocessing time, also the space is n log n. So we'll next have to work a bit harder to overcome this. In the next subsection, I want to talk about Cartesian trees. These will at first appear to have nothing to do with what we want to do, but they will then, in the next subsection, turn out to be the key technique to achieve the ultimate RMQ data structure. So far, we've achieved an n log n preprocessing time and space data structure that has constant query time using the sparse table technique. And it seems without more sophisticated tricks like this one using the Cartesian trees, we're stuck at this superlinear preprocessing time. So what are Cartesian trees? Remember again that our arrangement query problem has a relation to trees that we've already established, namely when we were looking at the motivation of the problem. We talked about the arrangement query on the longest common prefix array for suffixes, and how that corresponded to the lowest common ancestor of 2 leaves in the suffix tree. Now that's quite a stretch of topics, and suffix trees will not come to our rescue in this case, but a much simpler construction actually does. And I want to illustrate this on an example before we start. Suppose we have an array here, And for this section, I will, so this is maybe a warning I should make here. I want to switch to range maxima instead of minima. The reason is only it makes the pictures nicer by allowing me to draw a bar that is as high, or a pole that's as high as the value in the array. Whereas with minima, I would have to negate everything, and so this is inconvenient. But of course, when I can solve range maxima query, I can also solve range minima query by just negating all the values or reversing the order relation. The two problems are the same, they're symmetric. It's very similar to when we were talking in Unit 2 about the priority queue ADT and heaps. We also had the observation that the same tricks work for a minimum-oriented priority queue or a maximum-oriented priority queue. As long as you don't mix the two together, it's easy to have either one or the other. And the same is true for arrangement queries. You can use the same tricks to get range max if that is more convenient for your purposes. Or the other way around, I'll explain what Cartesian trees are for the range maximum problem. And the same trick applies to the range min problem. It just depends on the application, which is more natural to define. For the longest common extension queries, you need the minimum. That's why I introduced it that way in the first place. Okay, with that warning aside, here's what I did. Here's an array of numbers. And to make this a bit more graphic, I just represented these numbers as the height of a pole. What does that have to do with range maxima? Well, I can, if I have a range maxima query, first of all, just on this example, as before, so range max is the index of the maximum in that range. So what I do is I start from plus infinity and slide this line down. So I'm moving a bar down, and I can continue doing this until I hit. So here I bump into this pole, and that pole is the highest, obviously. So the position of that pole, that will be 9, because that's the first pole I hit when I slide down the line, just stretching the range that I'm interested in. Okay, that's just a reformulation of range max in geometric terms, if you like. Okay, so here's the solution. And again, this is what we had before. The task in all of this is pre-process the array so that you can answer a range maximum query fast, ideally in constant time. That's what we will be after. That's all repetition. Now, when things get interesting, by making the following observation, and this will appear to come out of nowhere for now, but let me just define it, and then it'll make sense at the end, I think. Let's define a binary tree as follows. We put a root node at the highest pole. So suppose initially we have a line covering the entire range, and you slide this down, and the first thing you hit, that will be the root of your Cartesian tree. Now, after you hit this root, you have two lines, the one that's on the left and the one that's on the right of this root, and you slide them down independently until they again bump into a pole. And that will be the next nodes of your Cartesian tree. So you connect these and make them the children of the root. That's what I did here nicely. Notice that what I put inside of the nodes is just the index in the array. That's just to help us distinguish the nodes. We will not need these labels at the end, but for now, this is what they are at the moment. Okay, once you've hit this bar, the bar is again split. Now you have a range between those two nodes. You have a range left of that. And there's actually nothing left. This is all empty, so nothing happens anymore. And again, these lines slide down individually until they bump into the first pole. and then you get the next round of nodes. Okay. I guess it's kind of clear how this continues. And that way you can define a binary tree that has one node for every position in the array. And it, in a sense, it nicely follows the structure of these heights just by the way it's defined. Okay. So far, so good. Let me briefly pause and give you a chance to ask questions about this. Is the definition of this Cartesian tree clear? How it's constructed? Rephrasing what I just said, you can take your array, you find the maximum in the array, and that splits your array into a part left of that maximum and right of that maximum. And so independently for these two parts, you construct the Cartesian tree and attach it as the two children left and right of the root, which is sitting at the maximum position. That's another way to say what I've just shown you on the example. Just a more algorithmic formulation maybe, but otherwise it's really the same. Okay, if that's clear, then let's move on. And here I need the full screen. How does that connect in any way to range min queries? It does through the following observation. If you have a range max, sorry, I'm saying range min, but I mean range maximum query in this subsection. If you have a range maximum query like this, 6 and 14, the one that is shown here in red, let's suppose we don't really look at the array, but we look at the tree only. We can find that there are two nodes, this one, 6 and 14, which are which correspond to the arguments in the range max query. And they're also the outermost nodes in that range by the index. So two ways of saying the same thing. You can find the two nodes that correspond to these indices I and j, the range, well, the outermost nodes in that range. And then the range max query is simply the lowest common ancestor of those two nodes. In this case, you have to walk up to root to this node 9 before the paths to the root meet. And that means that is the range max query. Okay. Now, the cool thing about this is, why this is really helpful, is that it also works if I take away the array. What we need now is only the tree, and we find those common ancestors. I didn't really look at the array to find that 9 was the lowest common ancestor of these two nodes. I just kept walking upwards, and then at some point they join, their paths join, and the first node in where they meet, that is what I return. That's the lowest common ancestor. Now, there's still a little trick we can play. So this, first of all, is just drawing the tree differently. Here it was drawn where the height of the nodes still encodes the entry in the array, but we don't really have the array in mind. What we have is just the tree. So this is ignoring the previous heights. This is just the topology of the tree. Of course, that doesn't change the relation between children and parents, so we can still find lowest common ancestors in the same way. And finally, we also don't have to store those numbers, 6, 14, and 9, because these are just the in-order numbers. So we can find those by doing an in-order traversal, which means we start at the root, then we always do first the left subtree, then we visit the root and put its number in, and then we go into the right subtree. So we do an in-order traversal, and number nodes as we visit them. So we start at the root, first go into the left subtree. That is the left subtree. We have another root. We first go into the left subtree. That is the left subtree. There's another node. Go into the left subtree. That's the left subtree. And I keep repeating this until there is no left subtree. And so this node gets assigned 0, the first index in the traversal. So if you want, we walk on the outer side of this tree down until we have to turn around, and then we put in the number. So here again, we have to turn around. So we have finished with the left subtree. Then comes the root of this tree, put in a 1, and then continue. Again, here we have to turn around, no subtrees. So after 1 comes 2, and then we walk back up. At this point, we have finished processing the entire left subtree of that node. So that gets the next number. I'll do a few more, but then I think you get the picture. So we finished the left subtree. So we put now a 4, the next number, into this node before we continue into the right subtree. Here we walk further down. There is a left subtree. We visit that first. Now we have to turn around. So the next number goes into here. We move up. We finish the left subtree. So the next number goes here, and so on and so forth. So you continue to walk around the tree like this. Something we've seen before. And that way you can compute these numbers that I wrote into the notes on the fly. You can reconstruct them. You don't really have to store them. It's enough to just store how the tree looks like, which means which nodes have left and right children. That is enough to answer the range minimum queries. In a sense of encoding. If you wanted to tell someone what is the range max, what is the range maximum of 6 and 14 in this array, you could send that person an encoding of this tree, and that would be enough. Then you just tell that person, do an in-order traversal, annotate all the nodes with their in-order rank, and then go to the nodes that have rank 6 and 14 respectively, find their lowest common ancestor, and that's your range max. Good? That's a Cartesian tree, and let's see if you're following on this one. So here's a little task for you to practice this. Here's a little Cartesian tree. And your task is to answer this range min query on this little tree. So suppose you're actually in this situation now. Someone sent you just a description of this tree and the two numbers 1 and 5. And you're supposed to tell me now what is the range max query. So this is max, right? Range max of 1 and 5. I'll give you a minute to think about this and try it out. You might want to do it on a piece of paper. The example might be a tiny tad too big to do it in your head, but maybe you can actually do it. Yeah, I drew the tree in a convenient form. So if you notice that structure, it's actually easy to do without a piece of scrap paper. I'll give you a minute to think about it, and then I'll show you. For those of you who didn't see how to do it, I'll show it in a second. I see some answers coming in. That's great. We had 16 votes initially for the programming puzzle, so maybe we can get something closer to 10 at least. Maybe if you're entirely lost and you don't feel you have any clue what I'm asking, maybe just let me know, because then your vote counts and we can move on and I can show you what how it works. But if you want to figure it out, we're not in a rush. It's fine to take your time. I'll leave the tree up for all of those who are trying to do this. I'll wait till we have 10 votes, and then I'd move on. In case this is relevant, remember we start counting in arrays from 0, and the same for the in-order ranks. Okay, we have 8 votes now. Maybe we can get 2 more, and even if that is 2 more, I don't know. That's fine. We're stuck at 8. Maybe we can get 2 more. I guess the good news is that you might actually be still thinking about this. There are more people tuned into the live stream. So I suppose some of you are still working on this. But then the 8 people who have already voted are bored. So maybe I'll give you 1 more minute, but then we should move on. Can we get 10 votes? Okay, I declare time's over, and let's move on, despite the fact that we didn't get the 10 votes full. But at least according to my watch, the minute has passed. Last minute in. Great. Okay, so let's lock this one now. I don't have to show the votes, you see it on the right, but maybe just for the sake of showing it on the video. Oh, you don't see the votes. That's a good point. And we can change that. So here are the answers, and there seems to be consensus about 3. That looks good. So let me briefly go through this without spending a lot of time on this little example, but okay, so the first step is to annotate the tree with in-order numbers. So we go all the way left, right? We walk around this tree, so that gets 0, then 1, then 2, 3, 4, 5, 6, 7. If you paid attention on the last slide, it was actually the way I drew this tree conveniently is so that the numbers here, 1, 0, 1, 2, 3, 4, 5, 6, 7, etc., they're just in left to right order. If you slide a line, a horizontal line from the left to the right, you encounter the nodes in order. In order, haha. And that's what's also happening here. Then we mark node 1 and 5, so these are here. And then we find their lowest common ancestor. And obviously, if I walk to the root from these two, I would meet in this node. So that is the answer, number 3. Good. Another way to show this would be to reveal that, so let me go back and forth on this a couple of times. There is an underlying array for this. There are many underlying arrays that give rise to the same tree, but here's one. And so just to convince you, you get this tree from this array, for example, and then the range min in this range from 1 to 5 has, range max, of course. The maximum in that range is at position 3, so hence 3 is the right answer. Okay, good. I hope this little example woke you up and showed you another time how Cartesian trees encode the range max queries and equivalently range minimum queries, but only one of them. And in a way that doesn't even talk about numbers anymore. It's only talking about trees and lowest common ancestors and in order numbers, but that's intrinsic in the tree, so we don't have to store them. Good, yeah. If you want to see a slightly larger example of a Cartesian tree, here's an array. So these are the values, and then I first drew the nodes at that height. So you see the maximum here is the root, because 30 turned out to be the largest number in this array. And then you get a nice graphical correspondence. Zooming is always a bit finicky in this one. So you get a nice picture where here I drew the lines that are sliding down. You start with the large horizontal line until it bumps into this pole. The highest is for 30. And then that gives you a vertical split all the way down. And then this line continues sliding down independently from the other one, and it bumps into the 27 on that side, whereas the other half bumps into the 29 here. So you see how this is grouped, and how you move down, and it probably also the vertical line just visually helps to see what's going on. Well, to be totally honest with you, I drew these pictures because I did research on this topic, and so I had them available anyways. I wrote programs to do these, so I included them. I don't have much else to say. I just wanted to show a bigger example to show off a bit. So here's one Cartesian tree for this array. If you draw the same tree in a more typical way how we would draw trees, you would essentially push the y-axis, the y direction a bit together. So it's the same tree, but now whenever you go to a child, you go one step down in y direction. That's the only difference between those two. And if you want to see the tree a little clearer, you might want to remove these separating lines. And so here's this tree again. But that's really all on this slide. All right. So now we've seen and understood what a Cartesian tree is. You might still wonder how that helps for an efficient algorithm, because so far it looks like you would have to first annotate this tree with all the in-order numbers, and that takes linear time. Then you have to somehow find a smart way to find lowest common ancestors. In fact, at the time in Unit 6, we said we can reduce the LCE problem, longest common extensions, to lowest common ancestors in suffix trees. And at that time, we said, here's a fat black box, a magic solution that does lowest common ancestors in constant time after preprocessing. And now we've reduced our range min query problem to lowest common ancestors. But somehow that's the wrong direction. Range min queries look, if anything, easier to solve than lowest common ancestors. And that's totally true. In fact, usually people use range min queries to solve lowest common ancestors, not the other way around. Now, so it looks like this Cartesian tree is a nice theoretical construction, but might not help you algorithmically too much. At this point, I agree. I will disagree later on, but we'll only get there after the break. There's one thing we can do with Cartesian trees, though, immediately, and that is counting the number of different solutions. And for that, they're really, really instrumental. The key observation that I hope you took from the examples that we went through is if you fix the Cartesian tree, you can answer all arrangement queries. Interestingly, the same is also true in reverse. If you have an array and you know all the answers to all the range min queries or all the range max queries, one of them, that is enough to construct the Cartesian tree. It's maybe not so surprising because you take the entire range, that gives you the root, and then you just recursively construct the roots of the subtrees. But that's beside the point, not really what I want to go into here. What I want to use this fact for is to count the number of different instances for the range max problem. Because we can instead just count the number of Cartesian trees. And Cartesian trees are simply binary trees, and that's all. And binary trees are well studied, so people have counted them. In particular, if you have n nodes in your binary tree, it turns out that this is exactly the number of different binary trees you can construct from n nodes. So, for example, if n is 3, how many binary trees can you construct with 3 nodes? There's this one, there's the opposite one, there's the more balanced one where you have the middle one in the root, and then there's the 2 zigzag ones. This one, okay, let me maybe move over here and let's make this so that we can fit them both in here. And the mirror image of that one. These are the 5 binary trees made from 3 nodes, and you can work out that this formula correctly predicts that. I don't want to do that now. I also don't want to discuss why this is correct. I think this is something worth knowing as a computer scientist. The Catalan numbers count the number of binary trees of n vertices and nodes. What I want to show instead is that we can encode a tree easily with 2n bits. So there's at most 2 to the 2n binary trees. And that means if I want to encode them, I have to take the binary logarithm. So if I wanted to specify one of these 5 trees, I could try to do this in a smart way, but I can also just take 2 times 3, so 6 bits. Might be a bit wasteful because 5 is less than 8, so for small numbers, here you could specify one of the trees using just 3 bits. I actually allow you to take twice that. But as n gets bigger, these two things get very close. So the waste in this simple code that I want to present to you becomes less and less relevant as n gets bigger. So let's see how we can encode a binary tree in 2n bits. What I'll do for that is, let's take this one as an example first. Maybe this one is slightly more interesting. Okay, let's do them all. Maybe that's better. So the code goes like this. We do a pre-order traversal. And then we encode for each node in 2 bits whether or not it has a left and right child. So we have 0 says no left child. The one here says but a right child. Okay? And pre-order traversal is important. That means we walk down the tree and we visit the root first. So the code for this tree would, we start here, then this gets rank 0, then we walk down the tree, this gets 1, we walk down, this gets 2, we walk down, this gets 3, then we return and walk down again, that gets 4, walk up, return, go to the next subtree, that gets a 5, 6, and then we walk all the way back up. We have seen everything in the left subtree now, so we continue in the right subtree only then, and that gets a 7. And to encode this tree up here, what I would do is I concatenate all these 2 bits for all the vertices, for all the nodes. So 0 has a left and the right child, so it's represented by 1, 1. The next node is again binary. It has both children, so we have another 1, 1. The 2 is also binary, has both children, so another 2 1s, okay? And then the 3 has no children at all, so it gets 2 zeros. So you can always take 2 bits together, specify one node, and this is 1, 0, 1, 2, 3, and so on. Let's briefly finish this off just to have a complete example. 4, 5 has no left but a right child, so that's 0, 1. 6 has nothing, and 7 has nothing. Okay, so that's easy enough. Now you might wonder if you can decode this. And the answer is yes, you can. By doing a pre-order traversal and constructing the tree while we're doing this. So suppose we didn't see this. It's hidden. And we can actually do that. So we only have this code. And let's construct the tree step by step. First of all, we create a node. And we attach 2 portals, 2 little beginnings of an edge, because 1, 1 says it has both children. And then we keep constructing in a pre-order traversal the next node. So first of all, the next node is again one that has both. And the next slot in a pre-order traversal of our tree is this one. So we take that one and put it here. Okay. Then we create the next node. It's again a binary one. So we create one with 2 slots. And we put it in the leftmost position that's free in the tree. You see how this goes. The next one is a leaf that has no slots. So maybe we mark this as finished. So there's nothing, or maybe even put like these little null pointers here. So these are to mark the fact that there's nothing happening. And again, put it in the leftmost slot that's free. The first slot you encounter in a pre-order traversal. Now we've gone through all these. We have 2 more leaves. This 1 more leaf that goes here. The next slot, so we move up. The next slot here corresponds to the 0, 1. So it doesn't have a left child, but it has a right one. Then we have 2 more leaves. We add them here, and here, and here, and here. And there is our same tree again. So we can encode and decode. 2n bits are enough to specify a binary tree. And this is a simple encoding that one can use for that. So far, so good. Let's see if you were following. And this one, I'll only leave it open for a shorter time because I want to get to the last topic today as well. So let's briefly see if you were following on this one. Here's a smaller tree, and I'm asking you to encode it in using the same code I just used on the bigger example. And you only have to encode it. We don't do the decoding here. So the code again, do a pre-order traversal and store for each node the 2 bits. Does it have a left child? Does it have a right child? Yeah, first answer looks good. Maybe we can get a few more just for the fun of it. And maybe, yeah, while you're still typing, I'll prepare the solution. So we walk around the tree like this. We first see this node, then this node, then this node, then this node. And we have to concatenate all their types. So 0, 1, 2, 3. And clearly 0 has both children, so that's 1, 1. Node 1 has a left but no right child, so that's 1, 0. 2 has nothing, 3 has nothing, and that is it. All right. I'll ignore the fact that not everyone has had a chance to answer. But yeah, so this is the result. The code itself is not that important for what follows. This is, again, a neat little thing to know as a computer scientist, how to encode a binary tree succinctly. But because the remaining section will not really rely on specifically that code, I'll just leave it open. Okay. With that, I want to come to the last subsection of this unit. I think that the 20 minutes that remain might actually be enough to finish this topic off. So if you've been enjoying this unit so far, that's great. And I think the topics up to this point are still somewhat of reasonable complexity. This last subsection is a little dig deeper into research level data structures. So this might be a bit of a tougher ride. And I would say a typical student at your stage might have a tough time following this when he or she sees this the first time. You might have to watch this video again. Let's just, with that warning, let's just ignore frustration if you have trouble following the first time. If you do follow, even better. I just want to show you this nice little result to give you a glimpse of what this looks like. All right, here goes. In this last subsection of this unit, and actually the last subsection of our module, I want to show you a trick that uses the facts we learned about the Cartesian trees to finally get to this optimal preprocessing time and space data structure for range minimum queries. And that uses the so-called 4 Russian trick. And at that point, I want to include a little disclaimer or a little, well, rectification if you want. It's about an algorithmic technique that was published in a 2-page paper in the 70s in Russian by Arlazarov, Dinitz, Kronrod, and Farachev. I'm probably not pronouncing them correctly, but I tried. And they all worked in Moscow at the time, but as far as I know, 2 of them are Russian, and the others, at least Dinitz is Israeli. He might have been Russian at the time, I'm not sure. And I didn't find information about the last one, Farachev. It's just not clear if they are Russians. And unfortunately, American authors, ignoring that fact, use this method of 4 Russians nevertheless. And not giving them the honor of mentioning their name is worth enough, but it's also factually wrong because it's probably not 4 Russians. Unfortunately, the name, it got stuck because it was coined at the time when, well, 70s, you remember what happened in history at the time. It's not relevant for algorithms now, but this name is not great, but it's in so wide use now that people kind of gave in and kept using it. I wanted to give this little credit to the original authors, nevertheless, without just mentioning their nationality or their place of work at the time. Okay, first step in this solution, in this more sophisticated solution for the range min problem, is taking what we have and see what we can get with simple tricks. Ignore the picture down there for a moment. What we've seen is the sparse table solution is an n log n time and space preprocessing solution that gives you constant query time, but the n log n is not quite as good as we wanted. However, if we apply it to a smaller subproblem, one that has only n divided log n elements, so we apply it to an array of only m elements where m is chosen like that, then m log m, the log n cancels, so that's linear then. So we can apply this simple solution, even though it's suboptimal, we can apply it if we just make our input a tiny tad shorter, a log n factor smaller. We've seen that trick before in Unit 3 when we were talking about parallel processing. Here we'll apply a similar trick, but to use it in a different way. So the first step is we break our array A into blocks of little b elements. And that number is carefully chosen. It will not make sense at this point why exactly it's log n over 4. It will make sense in a couple of slides. For now, what we do is we just break this array into blocks like so. For simplicity, I'll assume that there is no leftover block at the end, but that's a minor detail that you can handle if you want, or you fill your array with elements that are, if it's range min, bigger than all the others, so they never come out as a range min. So that's what you do, and that breaking A into blocks is only conceptual, but we can imagine that it's really consists of little blocks. Here it's 8 elements each. In our example, B is 8. But in general, it should be chosen like this. And now from every of these blocks, you nominate the smallest element and promote it to this small blue array, the B array. To be precise, we don't take the actual value there. Instead, we take the offset inside the block. So in blue here, I noted what is the offset inside the block. And if we know the block ID, so 0, 1, so maybe this is worth pointing out. So that's block 0, right? Maybe obvious, but let me write it down. Block 1, block 2, etc. up to block m-1. If we know the block, we can take that number and multiply with b, so that gives us the first position, and we can add the block local offset. That's the little blue number here. So our array B stores for block 0 what is the offset inside the block of the minimum in that block. So the blue guy is always the smallest elements only inside of this block. Okay? If you want, this is a little range min query in itself, where we exactly specify one block. Why do we do this? Because B now has exactly the size that's small enough so that we can use the sparse table on it without spoiling the overall preprocessing time or the overall space. B is chosen, or the block size is chosen exactly so that you can take this array B, it's not too long, it's shorter by a log n factor, so you can apply the sparse table technique on it, and we're still within our desired linear preprocessing time and, well, hopefully constant query time. We can do in constant time range min queries on this B array. It might just not make too much sense why we want to do this at this stage. Well, we'll come to that on the next slide. The next step here is we have a query that covers a certain range I to j. I drew this here in red. And remember, we imagine that our array is broken into blocks like so. How can we make use of the fact that we can use range min queries on B to answer this query? Well, first of all, notice that any such query actually covers 3 ranges. There's a certain part here. So this is this prefix. I don't want to use blue for that. So here's a prefix of that block that's covered. Here's a suffix. Sorry, that's the suffix. And here's a prefix of that block that is covered. So we have a part of a block at the end of the query, at the beginning and at the end. But then in the middle, we have a range of blocks, right? So for all but the leftmost and rightmost block, we know that we cover entire blocks. And that is useful because we can find the range minimum in this blue part using only the B array. Because any range minimum in this range will be one of these 3. It can only be a range minimum of a block that becomes the minimum of a range of blocks. Okay, it's a lot of ranges, I know. That's why I warned you up front. So what we do is we divide the query into a constant number of other queries. Remember, this is very similar to what we did for sparse tables. But here we have to be a little smarter in how to do it. We have one large range that scans entire blocks. That's this blue part. And then we have 2 little leftovers, but these are only inside a single block. So I'll call these intra-block queries inside a block and inter-block queries with the spanning blocks. Okay. And now the fun thing happens again if we ask what is the result of the red range min query, the entire range. It can only be one of a few isolated points. It can be the minimum in the green range in this suffix of a block, or it can be the minimum in the prefix of a block, or it can be the minimum from the blue range. Now, the example here is a bit misleading. I would have liked to have this minimum outside. So let's suppose this is not here, but instead is here. What I want to stress here is the minimum of this green range need not be a block minimum. And the same for this one. Whereas for the blue ones, we span the entire block, so it can only ever be a block minimum. Now, what is more precisely, what are the 3 ranges? We can express that using other range minimum expressions. So in particular, this first one is that first range min query. It only looks inside this block L. L is defined here, so you can just compute that from the query index. So we look inside one block, and within that block we have a certain range that we span. That's the green part here. We have the second green part down there. It's the same thing, just in a different block and with slightly different indices. And then we have the blue part, and that it looks a bit more complicated, but that's only because this array stores the block local offset and not the actual index. So we take the block offset, that is this expression, and then we add the offset from the block where we find it. So this is, you have to work out this in detail so that it makes sense. This is the block local offset. This is which block turned out to be the minimum, so that gives you the block ID. Maybe this is a good annotation at this point. That's a block ID. That is a block local offset. And from those 2 things together, you can compute the candidate minimum from the blue range. Okay? So it's not necessarily important that you follow the nitty-gritty details of how the indices are chosen. The important thing here is that you can take your query, the red range again, and you can represent it as 3 different queries. And then the minimum of the entire red range is whatever gives the smallest value from these 3 candidates. So that can be done in constant time if we are able to find these 3 candidates quickly. So that's what's stressed here. If we can compute interblock queries and intra-block queries, then we can compute these red ones. And we only need constant time for that. We compute the candidates. If that's done, we have a set of 3 possible positions in A. So we just look up into A what is the smaller one, and we return that index. And indeed, the blue range we've already solved. That was the previous slide where we discussed that this B is actually small enough so that we can just use sparse tables on it. So that's done. The only thing that's left is the intra-block queries. So we've reduced the entire problem, range min queries on a full array. We've reduced that now to only solving the little subproblems in a tiny range, just log n elements at most. It turns out that is the tough part though. And you have to apply a trick to get these. So the intra-block queries remain, and we want this time overall. The challenge is that we have almost as many blocks, so we can really only spend log n time per block. And we can also just spend log n space per block. And we have to be really careful with that. Whereas if we wanted to store the Cartesian tree in a way that it's easy to, well, it doesn't seem possible in an easy way to store the Cartesian tree so that you can find the LCA efficiently. And the trick is we don't have to. So we have many, many blocks, but they're all fairly short, just B numbers. We also know that we can encode the Cartesian tree for such a small range using 2B bits. And we've counted that the number of different Cartesian trees is not that big. So if we insert what we know about B in here and compute, we find there's only root n different Cartesian trees, even though we have almost n blocks in total. So we have n Cartesian trees in total to store, but only root n are different possibilities exist. So that means many of these Cartesian trees are actually identical. They look exactly the same. So how can we make use of that? And that is what the 4 Russian technique comes down to. We take each subproblem and represent it by its type. So that's a local encoding of the Cartesian tree in our case. And we will use this 2-bit encoding that I've shown you. Then we enumerate all possible subproblem types. There are just root n of those, so we can just pre-compute them all and store them in a big table. And then use the type as a lookup, as an index in that big table. So that's, in a sense, instead of figuring out a smart way how to solve these many instances, we just solve a problem that's simpler because there's few different Cartesian trees in total. There are not so many to choose from, so we can afford to just pre-compute them all. And let's briefly see how this is done. The preprocessing does 2 steps. The first one is for every block we compute the encoding of the Cartesian tree. That is easy to do in linear time. I don't have time in the lecture to show it, but it's actually fairly simple to do it. There's a stack-based algorithm to compute the Cartesian tree, and then a traversal of the tree gives you the encoding. We manually simulated that. And then you use these codes and store them. So you have an array. For each block, you store the code in the Cartesian tree. And the second big thing you do is you store one big lookup table where you have an entry for each block type. So suppose there's one entry, suppose that B is 4. Then we have one entry for this tree. We already know the block type for this tree was 3 1s and 5 zeros. That happens to be the encoding of that tree. Remember the clicker question. And then we have entries for all possible RMQ queries that are possible inside this tree. So there are actually not so many in this case. I think this should be all. And we can just look up what the numbers are. So this is 0, 1, 2, 3. The arrangement between 0 and 1. 1 is higher, so this is 1. 0, 2, it's 2. 0, 3, it's 2, because that's the root. 1, 2, 2 is the root. Whenever 2 is contained, it's the answer. So it's 2 in almost all cases. That's a fairly boring little example, but that's how it works. And you fill this table for all possible trees of B nodes. You just pre-compute them all and store this in one giant array. Okay. Now, this is good enough because the number of block types, the number of different entries in the first column is only square root n. That's what we just computed. The number of combinations of these columns I and j is b squared, and that's log n roughly. So we have square root n times log squared different rows, and that's a fairly small number. Even if, I don't know, if n is 1,000,000, this is a few thousand. So this is not very big. And we can also compute this efficiently. So with those two steps together, we bring down the overall pre-processing time to linear time by, instead of working out how to solve these small instances really, we do an exhaustive lookup table using the fact that there's only few different types. All these little instances of the problem can only be 1 out of square root n different shapes. And so we can afford to pre-compute them all and thereby circumvent the fact that just given the Cartesian tree, it's fairly hard to find lowest common ancestors efficiently. But if we have this lookup table, it's just a lookup. It's just an access in one big array. And putting that all together, I might have lost you in the process, but this is all the ingredients that you need to create a linear time pre-processing, linear space, constant time query data structure for arrangement queries. And with that, we've also solved the LCE problem in the same space. That was the last big open problem we left in Unit 6. So with that, we've brought the module to a nice conclusion where you've looked into all the black boxes that we used, and they seemed magic at the time. But now you can really look into this and understand the details. It is a bit complicated, I agree. Also to implement it, there's tricks where you can simplify it a bit and compromise on the theoretical guarantees. But the theoretical guarantees are best possible, and this is also a fairly recent result that I like very much. There's some open problems in this area where research is still ongoing, in particular about getting the space usage to the absolute minimum, or avoiding to have access to the array at query time. So a nice little twist on the problem is that you get the array at pre-processing time, but then I'll take the array away from you, and for the queries, you have to work only with your data structure, and you get no further support. You cannot look at the array anymore. If you're interested in these, let me know. Maybe we could do a project at some point. But for this module, I'll leave it with that. And sorry for going slightly over time. I think that's it. If you're up for it, I have some time for a little chat on Zoom. If you like that part or not, let me know. If you have any other questions about the upcoming assessments or something like that, we can talk about that as well. If not, I'll see you next Tuesday, 11 a.m. We'll use the usual lecture slot. They're timetabled in the usual way. I don't have more material to cover, but I want to give you a chance to answer the end of module survey, and we'll also talk about some exam questions. You will watch your inboxes. I'll send an announcement about that. Bye for now, and see you on Zoom if you want in a couple of minutes. Bye for now.